Hello everyone, today I will be trying to derive the formula for centripetal force, and also we'll be trying to see what the centripetal force actually is. So I've already drawn the figure at the left, and as you can see actually we are going to consider a uniform circular motion. Okay, we're going to consider first this uniform circular motion, which means that an object which is in uniform circular motion, it will have constant speed along a circle. Okay, along a circle, we can make this radius to be, we can consider this radius to be r, and the speed will be v. It will not change, and that's about it. That wraps up the uniform circular motion. And we can, as the velocity is, as the speed is fixed, then its angular speed is also fixed, which we can consider to be omega. Well, you can see it for yourself actually, because let's say in any time interval t, let's say it has gone this, okay, in dt, delta t, and let's say it has traveled delta theta in angular displacement. So the angular speed omega will be equal to omega average will be equal to d theta, delta theta delta t. But if we're going to talk about instantaneous angular speed, then it is going to be the limit as delta t approaches 0. So limit as delta t approaches 0, delta theta delta t, and we will consider it to be w instantaneous d theta dt. Actually, for any time interval we take, the angular displacement will always be corresponding to the time interval. Okay, so at any instant we take, the angular speed will not change. Okay, so that's it. And after that, what we can really do here is we're going to draw a circle. I've already drawn one, and let's say the body is in angle theta. So its x and y will be, let's say the radius is r, its x will be r cos theta and y will be r sin theta, right? And we already know that omega is equal to d theta dt, right? So if we are here to consider the radius vector, the radius vector will be equal to r cos theta I cap plus r sin theta j cap, and then we can differentiate it to find the velocity vector, which will be equal to r cos theta will be differentiated to be minus sin theta, and we have differentiated with respect to theta. So according to the chain rule, we have to differentiate it with the time as well. We have to differentiate it with respect to time. Okay, because we are differentiating both right and left side with time. Okay, so it's I cap. I'm not saying it's not differentiable. It's actually a constant, so it goes out of the differentiation. Okay, so it doesn't really affect the unit vector r sin theta. Okay, r sin theta, r is constant, sin theta will differentiate to be cos theta with respect to theta, so we have to differentiate with respect to t again. Okay, so j cap done, and we already know that this is constant, this is omega, so v will be equal to r omega minus r omega, minus r omega sin theta I cap plus r omega cos theta j cap. Okay, this is the vector sign, and we're almost done. Okay, what we can do right now here is differentiate it again to get the acceleration. The acceleration will be equal to, we have to, these are constants, and you know why I said omega is constant and why I used uniform circular motion. This is because omega must be constant. Okay, right now, right here, so minus r omega sin theta will be differentiated to be cos theta, and I cap will stay the same, and r omega cos theta, so we can differentiate it to, okay, my bad, I have missed one thing. I have differentiated it with respect to theta again, so I have to differentiate theta with respect to t I cap plus, because we are using the chain rule, so r omega cos theta will be differentiated, cos theta will be differentiated to be minus sin theta. Okay, and according to the chain rule, d theta dt j cap. Okay, So A will be then equal to, this is omega, so minus r omega squared. I can take the omega squared out, right? Okay, minus omega squared r cos theta item. And we are seeing another minus here, so minus another omega, so omega squared, then r sine theta j cap. And by some careful observation, you can see that we can take the omega square as a factor, and then we can see this, and you already know what this is. This is the radius vector, right? So acceleration is equal to negative omega squared r. Okay, so we have found the acceleration to be equal to minus omega squared r. So this is the form, and this is the centripetal acceleration. Okay, this is the centripetal acceleration, and I mean I can just paste it, right? You can always paste it. So if an object is moving in a circular path with a constant speed, then it will be necessary to have an acceleration which is, what is the direction? Negative r, which means it's in the direction of, I mean this is of course positive, and the direction is determined by r and this sign. So this direction is this. Okay, so this is the r vector, radius vector. So where is the negative r vector? The negative r vector is of course to the center, right? To the center, I mean origin. My drawing is so bad. Okay, I'm just going to use this. Okay. My bad. Okay, this should be good enough. This is r vector, and this is minus r vector. So of course the acceleration we need will be perpendicular, as r and v is tangential and r is radius, so it is going to be perpendicular to each other. Or you can use a dot product, of course. You can. Okay, you can just dot these two, v and a. You can dot these two, and you will find 0. So regardless, it's going to be perpendicular. You can do it mathematically as well. At any instance, the acceleration will be radially inward. It means radially inward. We need a force that's radially inward. Okay, so at this moment the force has to be here. Okay, of course perpendicular and towards the center. Okay, as we have taken the center to be the origin. Okay, that's why it's negative r. Okay, that's about it. Now we can see the, if the mass is m, then we can say the centripetal force is equal to ma, which is equal to minus m omega squared r. Okay, so centripetal force is equal to minus m omega squared r. There is another form, of course, and you can see that we have already drawn the figure here. Let's say this arc length is ds. Okay, so in time dt, this object has moved distance of ds, so the speed is equal to ds dt, right? So speed is equal to ds. We know that ds is the arc length, so ds is equal to has to be equal to r d theta, right? Because this is the radius and this is the angle that it makes, right? And this is the arc length that's associated with the angle. Okay, so this is r d theta dt. Okay, so d theta dt we already know as the as the angular speed. So this is r omega. So v is equal to r omega. Okay, so v is equal to r omega. V is equal to r omega. So we can replace omega with v divided by r. Now see, vcp is equal to, I'm going to draw the magnitude here first. I mean not draw but show. Fcp is equal to, the magnitude of this force will be equal to m omega squared, and its magnitude is r, so m omega squared r. Okay, and in this equation we can substitute omega to be equal to v divided by r square and r. For this radius vector, we can see that the unit radius vector will be equal to the radius vector divided by the magnitude, right? So what's the magnitude of this vector, right? What's the magnitude? Magnitude is equal to the radius, right? So divided by r. So we are also going to use that later on. Negative m v squared divided by r squared, r vector, and r squared we are going to distribute it here, not distribute, but we're going to just apply it here. R divided by R. So negative m v square divided by r, unit vector of r. So centripetal force is equal to negative m v square divided by r cap. So the direction is negative r cap, which is radially inward. Okay, this is radially inward. So that's the centripetal force formula we have got already. There are two formulas, right? So this is one and this is one. You can also say that from the first one, m omega squared, and the magnitude of r is r, and the unit vector, right? So unit vector r cap. Good enough. So what we really need is that the acceleration will be towards the center of the circle. Okay, that's the first thing we need, because not every time the circle will be the center of the circle will be in the origin. Okay, so of course. So let's just try to see a scenario. Let's say an object is moving along this circle, then at every instance the acceleration will be toward the center. Okay, toward the center. And also at any instance, if we consider a curve, you can, let's say you are at this point. Okay, so you can draw and you can approximate a circle here. Okay, you can approximate a circle here. If you approximate a circle here, then this velocity will be v. Of course, let's say v, I mean, let's just assume it to be v. Then for it to maintain the curve, it has to curve up, right? It has to change the direction. Right? So to change the direction of the velocity, you need a force, a centripetal force. The centripetal force will be directing towards the center. Okay, that's it. And of course, the magnitude of which will be mv squared divided by, let's say the radius is r, which you can calculate actually, r. That's it. Or m omega squared r, where omega is equal to v by r. That's it. So we will be using this extension. This was our main target all along.
Bye everyone. Thank you for watching. See you later.